All right, well, I'm going to start this meeting under recording so that you all can just access it. So we're going to cover this week descriptive statistics. So just a quick review. We're going to look at variables and measurements, and these are the scores and numbers that are the results of the observations, your empirical observations. And that the scores and numbers are results from a particular measurement procedure for each variable that you're interested to study. A quick review. So as I mentioned earlier in the first week, that there are 4 different types of measurement, types of variables. And you have to remember all of this because these are the basic rules in statistics. You cannot perform certain statistics based on the type of measurement that you have. So for example, nominal or categorical variables, you can only use chi-square statistics. And for ordinal or interval and ratio type of data, that there are specific rules as well, whether you can use ANOVA or we can use Mann-Whitney-U test, for example, for non-parametric. So it's really important to understand the characteristics of your data in order to use the appropriate statistics. And it's also to understand how many populations you're going to have in your study. Do you have 2 populations? Do you have 3? And subgroups of 3 different populations? So those are key important points to remember. So just a quick review again. Nominal are simply assigning names to the number. And these are characteristics of people, objects, or events. And we put them into categories. For example, if you have ethnicity, you can do 1 for African American, 2 for Caucasian, 3 for Hispanic, and 4 for others. And I'd like to emphasize here that we don't use letters. So instead of using A for African American, B for Caucasian, 3 for C for Hispanic, we cannot do that because SPSS and other statistical software can only do understand numbers or numerics. So the other categorical variables in the example here are gender, includes number 1 male, 2 female. Ordinal scale are those that are measured with numbers representing categories placed in a meaningful numerical order. So in our mind, these are typically those that are given values in terms of beliefs, values, opinions, point of view. And so, but there is no guarantee that the distance between the different values are exactly the same. These are commonly used in Likert type of scale, and also when we give our own opinions or evaluations. For example, the pain intensity, we know that if we can, we give the patient the option of 0, no pain, 1 for minor or little pain, 2 for moderate pain, and 3 for severe pain. We know that the distance from 0 to 1, and the distance from 1 to 2, and the distance from 2 to 3 are not exactly the same, that they are not very exact in values in between distance from different values of your scale. What about interval scales? Well, there's our scales where the intervals are exactly the same and between the values because the units of measures are equal in intervals. They do not have a true 0 as a base, but it is possible to add or subtract across an interval scale. This is considered as a continuous type of data and has a lot of applications for statistics, particularly different statistics such as t-test, ANOVA, if they are parametric or they have a normal distribution. Example of this are your SATs, that's the high school entrance exam here in the States, or graduate record exam, which is the graduate school entrance exam for those who already have a baccalaureate degree in the States. And then I think in the Philippines, it's the NCEE, or it might have another name by now. So what about ratio scales? So this is the highest level of measurements. The interval between the numbers are equal and they truly have a zero base and represents and determined by nature, and they are represented. There are two representative of the absence of the phenomenon. And an example for data for this type of scale, the ratio scales are your weight, your pulse rate, your height, your blood pressure. All of them, they true have a true zero as a base of value. So moving on, discrete variables, some of the terms that we use in statistics, discrete and continuous variables. Discrete has separate indivisible categories. No values can exist between the two neighboring categories. So for example, for the gender, 1 for male, 2 for female. So there's really no values that exist between the two neighboring categories. And then in comparison, when you have a continuous variables, there are infinite number of possible values between the two. Hi, Miss Mantus. Can you hear me, Miss Mantus? Miss Mantus, I'm actually recording this, so if you can hear me, just let me know. I'm recording this for your classmates, so I went ahead and did the discussion. All right, so I'm going to continue to just record, and I hope that Ms. Mantos can hear me. She just joined the conference. So continuous variables, again, as I mentioned, are those that have infinite number of possible values between the two observed values. It is divisible into an infinite number of parts, such as time, age, weight, and height. And when we do research, we're very interested in independent variables, the one that we can manipulate and the one that we try to plug in into our model. Independent variable usually, especially when we start creating models for prediction, especially in statistic 2, we try to determine associations first by doing correlations, because those with higher associations will likely result to a better prediction model. So independent variables are those that we identified as the treatment or the intervention, and independent as means that no other variable in the study should influence its value, that it can stand on its own. What about the dependent variable? Well, the dependent variable is the outcome variable. This is the one observed to assess the effect of, this is the one that we're trying to observe in relation to what is the effect of the independent variable. the dependent variable, because its value is thought to depend on the value of the independent variable, is our phenomenon of interest. So for populations and samples, I'd like you to study the video link. I've done a pre-recording on this one through screencast.com, and here's the link. So let's go to descriptive statistics. So what are descriptive statistics? Well, this is the basic statistics that are commonly used by researchers to report on populations and samples. It is used to describe, summarize, explain the different variables and measurements taken about a group of people or a group of samples. And by summarizing the information, descriptive statistics can speed up and simplify the comprehension of the group's characteristics. So think of so many numbers, and how do you make sense of all the numbers? And definitely the descriptive statistics is one of the basic and fundamental ways of summarizing numbers in order to comprehend the feature of a group. And so again, the purpose of descriptive statistics is to summarize, to organize, to simplify, and then to present the most important data of a particular feature of a group. So for example, here's an illustration. If you're presented with all observations on IQ, and the question is which group is smarter, and you can have a group, you have class A or section A of a class, and you have lots of observations for their IQ. You have 102, 128, 131, 98, 140, 93, 110, 115, 109, 89, 106, 119, and 97. And in section B or class B, you also have 13 students, and their IQ are 127, 131, 96, 80, 93, 120, 109, 162, 103, 111, 109, 87, and 105. So how are you going to answer the question of which group is smarter by just looking at these numbers? Well, descriptive statistics can definitely help you with that. By just simply doing the average and by doing the statistical power of descriptive statistics, you will get an average IQ of class A of 110.54, and the average IQ for class B would be 110.23. Then you can simply say that they're roughly the same, and that's the answer. So that's the beauty of descriptive statistics. It provides you a summary, and it gives you a quick answer, and it's a much easier way to answer the question, the question that's being presented to the researcher. So descriptive statistics look at frequency distributions, measures of central tendency, measures of dispersion, and variability. Now, I'd like you to remember that all of this frequency distribution, measures of central tendency, and measures of dispersions are all features of the population. And these are all features of what we call parametric statistics, because there's a parameter. These are the different qualities, characteristics of a certain population. So a certain population has a frequency of distribution. A certain population, they have measures of central tendency, which is your mean, median, and mode. And they also have the measures of dispersion, which is your standard deviation and standard error. And therefore, these are what we call the features or the characteristics of the sample or the population, and they're called parametric measurements. So they are bounded by all of these parameters, and they are bounded by all of these features or characteristics of the population. And so these are key concepts in parametric statistics. And as we move on with this course, we will be also covering non-parametric, and you will soon realize later that the non-parametric actually uses the median as a feature of in calculating their statistical value. So here's a good example. X is the ranking of the observations. So we rank our observation from 5, 4, 3, 2, 1, and F is the frequency. So we have observed that the top rank of 5 has 1 frequency, followed by 4, and has 2 frequencies, followed by 3, and there were 3 frequencies, and followed by 2, and there were 3 frequencies, and followed by 1, there's 1 frequency. So the frequency is the total number of observations, and so we can simply add that. And so we have in this slide, we see that our frequencies are 1, 2, 3, 3, and 1. We add all of that, and that's a total of 10, and that's our N, which is our total number of population. And in order to calculate the proportion, we simply divide F with the number of N. So if we ask what is the proportion of study participants that were having a rank of number 5. So we just simply say 1 divided by 10 equals 0.1. And if we convert that into percent, so how many percentage of the study population were ranked as number 5? And then you just say 10%. So, and you do exactly the same on the next column and then the next column. So it's very simple. In order to determine the total number of participants, or N, you just count the number of F, or the observed frequencies. And then in order to calculate for the percentage, you just simply multiply the proportion by 100, and then you get your percentage. So proportions and percentages. So proportion measures the fraction of the total group that is associated with its score. So in order to get proportion, it's mathematically expressed as P is equal to F divided by N, called relative frequency. They describe the frequency in relation to the total number of your sample or population. For the percentages, it's expressed relative to the frequency out of 100. So that's why you simply have to multiply the proportion by 100, and then you can express it into percentages. So here's a learning check. Use the frequency distribution table to determine how many subjects were in the study. So you have letter F right here. So that's the frequency. We simply count 2 plus 4, 6 plus 1, 7 plus 3, 10. So the correct answer is 10. So that's what frequency, or what we call relative frequency. Let's move on to measures of central tendency. The word central means middle or center. So it's a central tendency is a statistical measure to determine a single score that defines the center or the middle of a distribution. The goal is to find a single score that is most typical or most representative of the entire group. There are 3 ways to measure central tendency. That's the mean, the median, and the mode. So the mean is just simply defined as the arithmetic average of all scores in a distribution, whereas the median is the point at which exactly half of the scores in the distribution are below and half are above. So that's actually, you just need to count how many are in the study. You divide it into 2, and you find the middle. So it's you will look at where exactly are half of the group above the middle score, and where in the group where half are below the middle score. What about the mode? The mode is the most frequently occurring score, or the scores that that has the highest frequency, because again, it's most frequently occurring score or scores, and it can be more than one mode, or what we call bimodal, or even trimodal. So these are the things that we try to look at when we have a lot of data sets. We try to look at all these features of central tendency in order to describe our population. So again, the whole purpose of doing mean, median, and mode is to describe, to explain, to summarize, and in order to understand the population that we are trying to study. So the mean is very simple. It's the sum of all the values of the variable in a given data set divided by the total number of values. So mean is expressed as x bar is equal to the sum of the number of observed values divided by the n. So learning check, find the mean for the following sample of with an n of 6. So you have 4, 10, your observed values are 4, 10, 7, 5, 9, and 7. So you just simply sum all of that and then divide it by 6. So I think if by just doing our simple arithmetic, 4 plus 10 is 14, plus 7 is 21, plus 5, 26, plus 9, 35, plus 7 is 42, divided by 6, 6 divided by 42. So our mean would be 7. All right. So what are the characteristics of the mean? Well, the mean is a very, very sensitive number. It changes value every time you add a score. Every time you introduce a new score or remove a score, that changes the mean right away. Adding or subtracting a constant from each score also changes the mean. Multiplying or dividing each score by a constant multiplier or divides the mean by that constant also changes the characteristics of the mean. So the mean is very sensitive. So that's the message of this slide. So if you look at this, means can be badly affected by outliers. Data points with extreme values, unlike the rest, could definitely change the value of the mean. For example, if we look at the income in United States, and then all of a sudden we include the income of Bill Gates, and let's say if its income is 40 billion, and then the mean income of United States right now is about $65,000. So all of us will be in this curve right here on the left. And what happens is that if you add the income of Bill Gates, and if he makes $40 billion a year, you will definitely create a right skew or right skewness, and then it will pull your mean, it will make your mean even higher. So if the mean is around 67 in the left, it will make the mean income of the United States to almost like 200,000 just because you have one outlier, which is Bill Gates. So it is important that when you calculate for the mean, you have to remove the outlier. That's one of the things that you need to do when you are trying to calculate for the mean of the population, is you always check for outlier, and you need to remove that outlier in order to truly get the value of the mean. The next slide is the median. The median is the midpoint of the scores in a distribution when they are listed in order from the smallest to greatest. The median divides the score into two groups of equal size. It's very easy to look. If you have 13 students, if it's an uneven number, then you simply count the cases above and the cases below. So for this case, there are 13 students. So you're going to look at case number 7, which is considered as the median, because you have 6 cases above and 6 cases below for 13 students. So the median for this would be 109 for IQ of students in a class of 13 students. So if the recorded values for a variable form a symmetric distribution, the median and the mean are identical, and that's what we call parametric or symmetrical distribution, or it has a normal distribution. And if you look at this first curve on your left, it has a really what we call the bell curve appearance or bell shape. Now in skewed data, the mean lies further toward the skew than the median. For example, as I mentioned, if we include Bill Gates and our data will become right skewed, what happened is that the value of the mean will be higher than the value of the median because we have an outlier extreme to the right. That whole outlier, you can also have a negative outlier. So for example, if you're in your study, you're studying a lot when you study income in a population and you're getting the sample from the low socioeconomic neighborhood, and that will make your data to be right skewed. And so what happened is that your mean will be in a right skewed data set, your mean could become less than the value than your median. So you do need to be very careful about the different features of your study sample. And so that's why it's important to get a true representation of the sample by making sure that you don't have a sample bias. And that means that you need to be very careful about identifying your population and then identifying the representative of your population, and that becomes your sample. So the sample is the representative of the population of interest. So the median is the middle score or measurement in a set of ranked score or measurements, and the point that divides a distribution into two equal halves. Data are listed in order, and the median is the point at which 50% of the cases are above and 50% of the cases are below, and that's also known as the 50th percentile. So I think at Cebu Doctors, there's a lot of argument when we have our midterm exam and our final exam. And the question is, are we going to use the mean or are we going to use the median for our passing percentage? That really is a toss of coins, and there's a lot of debate about that in academia. So the mean is the average that's defined by the distances and often is not the midpoint of the score. What about the median? It is the midpoint of a distribution defined by a number of scores. Both the mean and the median measure central tendency using two different concepts of the middle or the center. So it's really up to you, the researcher, to choose which one best represents your population or your sample. What about the mode? The mode is the score or the category that has the greatest frequency in any of the frequency distribution. This can be used with any scale of measurements. It corresponds to an actual score in the data, and it is possible to have more than one mode. As I mentioned earlier, it could be bimodal, it could be trimodal. So look at this data, look at this observation. So it's from the number of correct out of 10, you have 0 to 10, and the frequencies. So you can see here from 0 to 4, it looks like the first you have one mode with the highest frequency of 2 and 3, and that's the first mode that you can observe. And then you have another group of observations that scored between 5 to 10. And as you can see here, the highest frequency, the highest frequently observed observation is 9 and 10. And so that's your second mode, or what we call the peak observations. So learning check. During the month of October, an instructor recorded the number of absences for each student in a class of 20 and obtained the following distributions. You can see here the F, we have to count 1 plus 2 is 3 plus 7 is 10 plus 5 is 15 plus 3 and 2, that's 20. So we have an N of 20. So the number of absences is 5, 4, that's 9 plus 3, 12 plus 2, 14 plus 1 is 15. So when it comes to calculating the mean, we have to calculate the sum of all the observed values. So we have 15. So this is 5, 4, 3, that's 12, 14, 15, divided by the N. So 15 divided by 20, that is your arithmetic mean. And then when it comes to the median, so when it comes to the median, you just have to count the number of frequencies. So, so 5, 4, and 3. Remember that the median is the 50th percentile. So you count from the top. There are 6 reported here. So 1, 2, and 3. So 3. We stop at 3 and the upper, and then we count from the bottom, 0, 1, and 2. We stop that. So this is an even. So you actually calculate between the upper and the lower. So 3 plus 2 is 5, and so we have a median of 2.5, which is if we calculate. Let's see. Let me go to my calculator. So here, trying to remember 15 divided by 20. So 0.75 actually is our, that's the number of, that's our mean, because we have the sum of our, so we have the sum of our observed divided by the n. So we have 0.75. So can you imagine the mean for the group of absences for this class is 0.75. The median is 2.5. And then for the mode, you actually have 7 and 5. So there's such a big differences in the mean, median, and mode for this particular data set. So here are the different formula again. For mean, it's the sum of all the observations divided by the n. It is precise, but the cons for using the mean, it's skewed by outliers, and it may not be realistic to use the mean. I think in our example, it's also unrealistic to use because we have outliers. We have one observation that's 7, and then we have another observation that is 0. So that's why the mean doesn't seem to doesn't make sense to be our measures of central tendency for the example that we provided earlier ago. What about the median? Well, the median is, again, if it's odd number count from either direction, or if even average the two middle values. So that's why we average 2 and 3, and then we have a 2.5 as the median number of absences for the class. It's not skewed by outliers, so that's the beauty about using the median, but it's also not good if data doesn't cluster around the median. So each of these measures of central tendencies have pros and cons. And then the last one is the mode. It refers to the highest frequency, may not be in the near center, and it's imprecise and misleading. As I've mentioned earlier, our mode for the example that we just talked about is 5 and 7, because those are the highest frequencies, and those are the peak of the absences that's observed in that particular class. So I think the take-home message every time we look at pros and cons of measures of central tendency is to really understand our data set and to apply the appropriate measures of central tendency that would best represent our population. So the central tendency and the shape of the distribution, again, in a perfect world, we believe that there is a symmetrical distribution, that the data are evenly distributed about the center. And this is what nature is all about. There are always the good, and then you have your goods to, you have your not so good student, you have your average student, and you have your excellent student. And that's what you call the symmetrical distribution. Just like in IQ, it's quite symmetrical when it comes to intelligence. You really have a very good bell-shaped curve when you try to go to a, when you study the IQ of a population, it has a symmetrical distribution. So the mean and the median have the same value if there is a symmetrical distribution. So again, the same thing with IQ. Because it has a symmetrical distribution, you will see that the mean and the median, that they have the same value. If exactly one mode, what you will see is that the same value as the mean and the median also. So mean, median, and mode would become will be in the middle when you have a symmetrical distribution. And this is a feature of what we call parametric statistics, because there is symmetrical distribution, and again, there is the same amount of data on the right and on the left side of the distribution. And this is one of the hallmarks of parametric statistics, such as your t-test, such as your ANOVA, and again, such as your linear regressions statistics, which we will cover in the second part of this statistics class. So for skewed distribution, the data are not evenly distributed about from the center. Skew is usually mean minus the median divided by the standard deviation, and it could range from -1 to +1. For symmetrical distribution, the mean equals the median, and the skew is 0. This is such an important concept. The value of skewness is 0 when the distribution is symmetrical. So this will come out in your quiz. So you have to remember. So anything that's a positive skew means skewed to the right, and anything that's a minus value in the skewness. So when we do our printout for SPSS later, and if I will ask you a question, interpret the skewness value of your SPSS output, it's really very easy. Don't forget that the value of the skew is 0 if the mean equals the median. And so if there is, if the value of the skew has negative symbol to it, that means it's negatively skewed. And if it's positive, then it is positively skewed. So moving on. So this is in an illustration of what I have just mentioned. So what happens then is that the mean is definitely dragged and it becomes higher if you have right skewness, and the median has lesser value than the mean in a right skewed. In a left skewed, what happens is that the mean has actually less value than the median, and it is represented by this curve on your right. So think about that. If it's left skewed, the value of the mean becomes lesser than the value of the median. If it's right skewed, that's right to the right, the value of the mean is definitely higher than the value of the median. So these are different examples of skewed distributions. A positive skew, so you can see here the mean is 59.14 and the median, the value is lesser at 55. But what happens then if it's left skewed or negatively skewed, then the value of the mean right here is only 60.86. The median is 65. So the value of the median is higher in a negatively skewed or a left skewed distribution. What about kurtosis, or what we call the peak? How peak is the distribution? It's a very tedious calculation, but SPSS will do that for you. Kurtosis coefficient equals to 0 when the distribution is normal. It is rare to see kurtosis at the 0 value. So kurtosis coefficient is positive, and we call it the leptokurtic, or the peak. Kurtosis coefficient is negative when the distribution is flat. So here are the different illustrations. Leptokurtic, you can see that the bell shape is very, very perfect, and you can see the peak of the bell curve. And then you have mesokurtic. When it's normal, it is evenly distributed. And then you have platykurtic, which is negative, it's almost flat, when the kurtosis coefficient is becoming negative. What are the different measures of dispersion? Now we're looking at dispersions now, or variability. Again, I want to point out all of this: measures of central tendency, measures of dispersion or variability. They are all features or characteristics of the population that we are interested in studying. And these are the features that are used in parametric statistics, such as your t-test, your ANOVA, your linear regressions, and that we assume normal distribution in parametric statistics. All right, so let's move on with the last topic, which is the measures of dispersion or variability. So variability can be defined in several ways. This is a quantitative measures of the differences between the scores, the differences between the observed values in your experiment. They describe the degree to which the scores are spread out or clustered together. And the purpose of this is to really describe the distribution. How different are the observations that you have seen in your research? How intelligent is one one study participants from the other. So just like when you obtained a different IQ, so those are what we call the variability, because those are the differences of the scores of IQ. Those are the differences of the observed values that you have obtained from your research. It measures, so variability measures how well an individual score represents the distribution. And the good thing about looking at variability is that you're really able to point right away where that particular observation belongs to in when it comes to the entire population. So the purpose of measuring variability is to obtain an objective measure of how the scores are spread out in a distribution. At the same time, you're able to point out where is that observation in relation to the general population. So if you have, if we don't study variability, then we won't be able to say that Mr. So and so is very intelligent because his IQ is standard deviation plus 3. Well, what do we mean by standard deviation plus 3? Well, by just simply saying that, we know that in the standard deviations, our mean is considered as 0 value, and those that perform really well are standard deviation plus 1, plus 2, plus 3, and most of the time, standard deviation 2.5 to 3 are really the critical value, are those extreme scores in an observation. So when you have someone who have an IQ of standard deviation plus 3, really tells you that that's a very intelligent person, because he is definitely beyond the mean, because the mean is represented as 0 in the concept of variability. All right, so the purposes, it tells whether the scores are clustered close together or spread out over a large distance, and it tells us how well an individual score or group score represents the entire distribution. As I mentioned earlier, by looking at variability, by making a mathematical calculation of the normal distribution, by just simply saying that man is very intelligent, his score in IQ is standard deviation plus 3, that tells you right away, because we know that our variability, the means is represented by 0, and anything plus to the right and minus is to the left will be mathematically easily understandable for all of the readers. So why measures the spread or variability? Well, because sometimes averages alone are misleading. Two data sets can have the same meaning, but very different variabilities. So for example, for the year of 2010, you can have different set of data, and then for the year of 2011 you can have another set of data, because every year you have different levels of test takers in your SATs, for example, in the United States, or National Collegiate Entrance Exam in the Philippines. So you need to have a measures of variability, because it's very hard to compare apple from an orange if you have two data sets, but it will be a lot easier to make an interpretation if you have one data set and you actually study the measures of variability for that particular group of data set. Then you can make a meaningful comparison later on. And what we also know is that we can have a homogeneous group if scores in a distribution are similar and there are low variability. So that's what we call homogeneous population. At times, we can really have a very good group of a sample where the scores are really very high, and that the distributions are very similar and there's very low variability. So you can. This is typically seen in what we call magnet schools, where those who are already considered as A students are being sent by another school. And then, so you really have a group of really intelligent students. And by the time you take their IQ, then their scores are there in the 120 to 125. And so the distributions are very similar and there's low variability. So you need to be careful about that when you try to study and make sure that the magnet schools students are not being compared to the general population, because obviously they're already been self-selected, and those who are in magnet schools are being sent by another school because they are already considered as a student, or top 5% of the class. Heterogeneous are, this is what we call, scores are very different, and we see a lot of high variability. And this is one of the things that we also need to look at when it comes to measures of variability. Measures of dispersion. So um, the measures of dispersion shows us how much the data cluster or spread around the mean. So mean is a very important concepts when we look at dispersions. For example, here, calculate the mean of observations of 0, 0, 0, 0, and 250, then the mean of 50, 50, 50, 50, and 50. Both have means of 50 actually, but the nature of each data is very different, because dispersion look at where does the data cluster or spread around the mean. There are three measures of variability. The first one is the range, the standard deviations, and the variance. Later on, you will learn that ANOVA, analysis of variance, is all about studying variance. And then later on, when we look at t-test, it does look at the standard deviation a lot, and it uses the features of the mean and standard deviations, and a combinations of the different measures of central tendencies. So the range, or what we call the distance, is the distance between the lowest and the highest values of a variable. To get the range, it's very easy. You simply subtract its lowest value from its highest values. So for class A, which one is the lowest? Which one is the highest? It's 140. Which one is the lowest? It's 89. So 140 to 89 equals 51, and that's the range. For class B, then our highest is 162, and then our lowest is 80, and we have an 82 as the range. Standard deviations and variance are the most common and most important measure of variability. This is a measure of the standard, or the average distance from the mean. So think of it that standard deviations and variance uses the value of the mean. So it describes whether the scores are clustered closely around the mean or are widely scattered. Describes also the variability by measuring the distance between each scores obtained from the samples or populations and the mean. So here's a very good illustration of the variance. The top is that the larger the variance, the further the individual cases are from the mean. So you have a flatter bell curve appearance. The smaller the variance, the closer the individual score are to the mean, because the mean is in the middle. And remember, the mean is the center, or the middle. And so if the variance is smaller, that means that your bell curve will look a little bit slimmer, because the individual scores are closer to the mean. But if the variance is very large, so the observations from the different subjects are widely scattered, what you will see is a flatter bell curve. So the next slide here shows you population distributions for height and weight. So you can see here, adult heights in inches is that you have definitely a very tall, a very nicely shaped bell curve. As you can see here, this is normally distributed, and it looks like the variability is not very high. It's because a lot of observations are clustering around the mean of 70. Well, look at the adult weight in pounds. Well, the variability is it's definitely wider. As you can see here, from 110 to 230, and the observations are not clustering towards the mean of 170. And so you have a flatter a flatter appearance of the bell curve. So standard deviations is calculated in order to really have a mathematical representation of its observations of the sample. So to convert the variance into something of meaning, we need to create standard deviation. As I mentioned earlier to you, in normal distribution, the mean is considered as the center, and we put a value of 0 in the mean. And when we say standard deviation plus 1, it means that the score of that particular or the value of that particular observation is definitely higher than the mean. So it's so easy to understand mathematically if we use standard deviation. So how do we calculate standard deviation? It is simply the square root of the variance, revealing the average deviation of the observations from the mean. So here's how do we calculate. Sum of square is the sum of the square deviation of scores from the mean. And the deviation is the distance from the mean. As I mentioned, you just simply assign 0 as the value of the mean, and any deviations, if it's positive, it will be represented by a plus sign, and then if it's negative, it will be represented by a negative sign. So a deviation score is the difference between a score and the mean, represented by x minus the mu. So simply define as the average of the squared difference from the mean. So to get your variance, this formula is very simple. It's just the sum of the squared deviations divided by the number of the scores. So here's the definition formula. Find each deviation score. It's just simply the observed value minus the mu. Square each deviation score, such as x minus the mu, square that, and sum up the square deviations, such as the sum of x minus the mu squared the observed values minus the mu, and that is your sum of squares. For computational formulas, square its score and sum the squared score. Find the sum of the scores by squaring it and divided by the n. So right here is your sum squares. So the variance is simply the sum of squares divided by the n, and in order to get the standard deviation, you obtain the square root of the sum of squares divided by the n. So the goal of inferential statistics is to draw general conclusions about the population based on limited information from a sample. We can definitely make inferences by having at least limited information from a sample. What we know is that samples differ from the population, and that samples have less variability, but by computing the variance in the standard deviation in the same way for a population, might give you a bias estimate of the population values. So it's important then to understand that we need to obtain standard deviation and a variance, and then based on these two features of the sample, even though you have limited information from a sample, you will be able to draw general conclusions about that population. Because remember, when we study, we only have a representation of the sample of the population by obtaining a sample, which is as much as possible should represent the population of interest. So degrees of freedom, this is a very important concept in t-test and all of statistical calculations, including ANOVA, including non-parametric statistics. Is simply the degrees of freedom is a strong consideration, because with a population, you can always find the deviation of each score from the mean, and with a sample, must use the sample mean, which can understate the population mean. So how do we calculate the degrees of freedom? Well, the sample variance uses the degrees of freedom by simply calculating n minus 1. Because we lose a degree of freedom, we are estimating the population mean with the sample mean, and therefore it's a very simple calculation for degrees of freedom. It just simply means sample, which is an n, minus 1 is the degree of freedom. So continuing on the degrees of freedom, what we know is that in a population variance, the mean is known, the deviations are computed from a known mean, and that the sample variance is an estimate of the population. We can create sample variance if the population mean is unknown, and samples have less variability than the population from which the samples are selected. And to calculate the degrees of freedom, because we only have the number of scores in a sample that are independent and free, always varies. So our degrees of freedom are simply calculated by doing sample size, which is an n, minus 1 is the degrees of freedom. So if you have a sample of 20 minus 1, your degrees of freedom is 19. All right, so that summarizes this meeting. Ms. Mantus, if you have any questions,
Yes.
please feel free to do so.
No, I don't think I have questions. Okay, thank you very much.
All right.
It's kind of enlightening, kind of reviewing what we have in statistics before, but it's quite rather remote. So it's
Okay.
like
Awesome. Just remember that these are all foundations of parametric
yes,
statistics. Just make sure that the means, the median, the standard deviation, the standard error or mean, these are all features of our population of interest, and that, you know, these are parametric. These are the parameters. There's a low and there's a high and there's a middle, and that by knowing all of this, we can really make inferences. Okay.
yes.
All right. So I did record this, and hopefully I can share